And today we're learning something new. Yes, it will be. Okay, so I made a mistake on the worksheet that I gave you. So I'm going to have to find problems in the book here. Okay. So let's say that we have something like 2 sine squared x equals 1. Let's solve that to start with. Okay, I'm going to give you a couple minutes to do this. You should know how to do this one. So what do we do first? Divide by 2, right? So sine squared x equals 1/2, and then square root both sides. So sine x equals plus or minus 1 over the square root of 2, because the square root of 1 is 1. So that's actually plus or minus root 2 over 2. Bless you. So that means x equals the inverse sine of root 2 over 2, plus or minus root 2 over 2. Okay. So looking at our unit circle, where are the y values equal to plus or minus root 2 over 2? At all these 45-degree angles. So x equals 45 degrees, 135 degrees, 225 degrees, and 315 degrees. Okay? So now we're going to change it a little bit. We're going to add a little bit to it. And we're going to say, instead of 2 sine squared x, we're going to do 2 sine squared 2x equals 1. So this is solved the same way, right? We're going to do sine squared 2x equals 1/2. So sine 2x equals plus or minus 1 over root 2, plus or minus root 2 over 2. So the difference is at this step right here. So what we're going to do is take the inverse sine of both sides. And when I do that, on the left, instead of being left with x, I'm left with 2x. So now when I find the angles, instead of x equaling those angles, 2x is equal to those angles. So we have 2x equals 135. 2x equals 45. 2x equals 225. And 2x equals 315. So we do everything the same, except that instead of having x equal to it, it's 2x. So now I have to divide everything by 2. So x equals 135 divided by 2, which is what, 67.5? X is equal to 22.5. X is equal to 112.5. And x is equal to, thank you very much. So there's our answer. Okay, So it's the same way that you solved it before, except that when you get your answer, it's 3x that equals that. Questions on that one? Okay, I want you to try this one. Try cosine 2x times 2 cosine x plus 1 equals 0. Try that one by yourself. What should I do? No. Do what? No, I don't want to do that either. No? If I had x times 2x plus 1 equals 0, how would I solve that? Well, if I distribute, how does that help me?
You would do what's inside of c squares like minus the 1 thing divided by the 2 and then put a 0 for the x on the other side. Maybe. What? I know. It's the zero product rule.
Zero product rule, yes. Right? So we set each one equal to 0. Set each one equal to 0. Okay? So that's what we're going to do over here. We're going to set each one equal to 0. You were almost there, definitely. A couple of you were almost there. Yeah, you're not just subtracting 1, right? You're not just subtracting 1 because you've got to set it equal to 0 before you subtract 1. Okay. Okay, so let's deal with this one over here. Let's go ahead and subtract our 1 now. And then divide by 2. So x equals inverse cosine of negative 1/2. So what does x equal? Remember, we can use our calculator to help us get started, right? So if I do inverse cosine of negative 1/2, oh my goodness, you guys, bunch of sickies. Okay, so we get 120 degrees. So we can use our calculator to help us get started. So 120 degrees right here, that's one of my solutions. How do I find the other solution? Oh.
Yes, 240.
I want to subtract from 180.
Subtract 30 from 270.
Okay. Look at the reference angles, right? Look at the reference angles. Here's my 120. The reference angle is the angle with the x-axis. So let's find all of those reference angles. There's 120. There's 120. And I'm sorry, 60 degrees is the reference error. So sorry about that. So my reference angle is 60. So all of these have a reference angle of 60. Which one will have a cosine that's negative? This one and this one. So we're looking at 120 and 240. Okay, we use that reference angle. Okay. Okay, let's solve the other side. So I've got cosine 2x equals 0. So that means what? 2x equals inverse cosine, right? 2x equals inverse cosine of 0. So now let's look and see, where is the cosine equal to 0? At 90 and 270. So 2x equals 90 and 2x equals 270. So that means x equals 45 and x equals 135. So there's my answers. X equals 45, 120, 135, 240 degrees. How could I check that on my calculator? Graph it. Okay. Okay, so you should all have your calculator here out, and you should all be doing this. Okay, we're going to do cosine 2x times, what was the other one? 2 cosine x plus 1. Let me put this in parentheses. Insert parentheses. Times cosine x plus 1. Okay. What mode should I be in? Degree. Okay, let's look at our window. What should our window be? 0 to 360. And when I look at my answers, I've got 45, 120. So how do I want to break that up? If I do 30 degrees, it's not going to cross at 45. If I do 45, I guess I'm not going to get it to be perfect, am I? So we can leave it crossing each one at 30 degrees. So that should be okay. Okay, so let's see how many intersections do I have? 1, 2, 3. I have 4 intersections, right? 45 degrees. So each mark is 30. So halfway between 30 and 60, there's my 45. So 30, 60, 90, there's 120. 150, 180, 210. What's this one here? This is kind of in between the 210. Is that 240? Well, that doesn't seem like it, does it? I guess it's just the graph. Let me do a calculate 0. When you're looking to see where it crosses the x-axis, you're doing a calculate 0, right? Yep, comes out to 240. Just didn't look like it, but it does come out to it. Yes.
How much should the window be? Mine looks like a straight line.
Degree mode.
I'm in degrees.
Are you now? Ah, windowed. Make sure you get the same window.
That's what I was asking.
Yep. I thought you said mode. Sorry.
No.
Okay, if we're working in degrees, we're going from 0 to 360. If we're working in radians, we're going from 0 to 2 pi.
6.
Okay. And then you should get this graph. So that's how we can check it.
I'm not getting it.
Can I see it?
Yeah.
That's good. I'm glad you guys are doing this with your calculator so we can figure out what's wrong, right? Because you put inverse cosine of 2x instead of cosine 2x. Right. Anyone else having trouble?
Can I see what your window looks like? Yeah.
Anyone else?
Oh, I never do good on history tests. I get the
I'm just
covers
glad she
every
traveled
single
with
day in class, whereas I
Okay.
don't get 70s on the test. Good job, man.
They would have killed
What'd you get?
Cool. If you would have left that.
Okay, so this will be on your test on Tuesday. We're starting a new section today. Okay, so this will be on your test on Tuesday. Okay, so we're going to look at some more trig identities and formulas. Okay, these are called the sum and difference formulas. This is not on your test. Okay, you want to take a couple minute break before we do this? Okay, let's take a couple minute break. Mason, you can go blow your nose. Yes. No going to see the tree today. On it. Mason, did you get your answer?
Yeah.
Good job. Are we ready? Okay. All right. Okay, so let's see. What's this going to be? Cosine of 135 times the cosine of 150 minus sine of 135 times the sine of 150. Okay, so let's see. Let's look at our unit circle. Where's 135? Right here. Okay, so the cosine of 135 is good, negative root 2 over 2 times the cosine of 150, so that's root 3 over 2, negative, thank you, minus the sine of 135, which is positive root 2 over 2, times the sine of 150, which is positive 1/2. So we've got positive root 6 over 4 minus root 2 over 4. So that gives me root 6 minus root 2 over 4. Okay? Okay. They are harder when we're dealing with radians. So if I want to find the sine of pi over 12, the sine of pi over 12. Now, what I do is I kind of have to make a list of the radians that I know, right? So if you think about your unit circle, right, this is pi over 6, and then I have pi over 4, and I have pi over 3. So somehow can I combine those to equal pi over 12? So what I'm going to do is rewrite these using a denominator of 12. So this is 2 pi over 12, 3 pi over 12, and 4 pi over 12. When I do that, it becomes clear that I could rewrite this as the sine of 3 pi over 12 minus 2 pi over 12. Okay? So list the radians that we know, the common radians. Okay, I didn't bother with the pi over 2. We could have used that also. And then put them in terms of the denominator that we need. We needed a denominator of 12. And once you do that, it's not too bad. Okay? So our formula, right, sine of u minus v, that's going to equal sine u cosine v minus cosine u sine v. Okay, so we've got the sine of 3 pi over 12 times a cosine of 2 pi over 12 minus the cosine of 3 pi over 12 times the sine of 2 pi over 12. Now I'm going to go back and reduce those fractions. So this is the sine of pi over 4 times the cosine of pi over 6 minus the cosine of pi over 4 times the sine of pi over 6. So radians are harder to work with because we have to work with fractions, and nobody likes fractions. Okay? All right, sine of pi over 4, we know that is root 2 over 2. Cosine of pi over 6, well, pi over 6 is right here, so that's root 3 over 2. Minus the cosine of pi over 4, which is root 2 over 2, times the sine of pi over 6, which is 1/2. So we get root 6 over 4 minus root 2 over 4, which is root 6 minus root 2 over 4. And yes, they do usually come out to be something similar. You notice all the answers we've gotten have been very similar. Okay, up here we got, up here I erased it. Let's see. Over here I had root 2 plus root 6 over 4. This is root 6 minus root 2. So they all end up being very, very similar. Okay. Questions on that? Okay, so what if you were given something like this, a cosine cosine of 40 times a cosine of 15 minus the sine of 40 times the sine of 15. Can you write that as a single trigonometric expression. So I can think of this as cosine U cosine V minus sine U sine V. So which formula does that match? Cosine U plus V, right. So this is cosine U plus V. And in this example, what's the U? 40. So it's cosine 40 plus V, which is 15. So this equals a cosine of 55. Okay. So that's kind of going the other direction. We can start out with a sum like that and condense it to a single trigonometric expression. Okay. Okay. I think we're going to stop there for today. Okay, we did a lot. We're going to stop there.